Deep dive into scikit-learn's compound kernel for Gaussian processes. The compound kernel in scikit-learn's Gaussian process library offers a powerful tool for constructing complex kernel functions by combining simpler kernels. This enables you to model intricate relationships between your data and achieve better predictions. Let's delve into its intricacies. Understanding the basics. Gaussian processes GPs are a powerful non-parametric Bayesian method for modeling functions. They work by assuming a prior distribution over functions and then updating this prior based on observed data. Kernels are the heart of GPs. They measure similarity between data points, defining the covariance function of the GP. Different kernels capture different types of relationships in the data. CompoundKernel. This object allows you to combine multiple existing kernels into a single, more sophisticated kernel. This lets you capture diverse aspects of your data within a single GP model. Key features of CompoundKernel. 1. Combining kernels. Addition. Combining kernels with creates a sum of their individual contributions. This captures both the features captured by each individual kernel. Multiplication. Combining kernels with creates a product of their individual contributions. This captures interactions between the features captured by each individual kernel. Product. The product class allows for a more flexible product combination where you can specify weights for individual kernels. Sum. The sum class offers a flexible addition combination where you can specify weights for individual kernels. 2. Flexibility and control. CompoundKernel allows you to define a hierarchical structure of kernels, creating complex combinations. You can easily adjust the weights of individual kernels to fine-tune the model's behavior. You can use different types of kernels within the compound structure, enabling you to model a wide range of relationships. 3. Advanced features. Kernels attribute accesses a list of the constituent kernels within the compound kernel. Hyperparameters attribute returns a dictionary of all hyperparameters present in the compound kernel. NDIMS attribute specifies the dimensionality of the combined kernel. Bounds attribute accesses the bounds for each individual hyperparameter within the compound kernel. Applications of CompoundKernel. Modeling complex relationships. Use different kernels to capture different aspects of your data, like spatial correlations, temporal trends, and nonlinear interactions, improving model accuracy by capturing a wider range of features. Compound kernels can lead to more accurate predictions. Customizing model behavior. Adjust the weights of individual kernels to emphasize certain aspects of the data or to control the smoothness and complexity of the GP model. Example code. Python. From sklearn, Gaussian process import Gaussian process regressor. From sklearn, Gaussian process, kernels import RBF. Constant kernel. CompoundKernel. Define individual kernels. Kernel 1 constant kernel 1.0. Constant value bounds 1e-3. 1a3 RBF 1.0. Length scale bounds 1e-3. 1a3. Kernel 2 constant kernel 1.0. Constant value bounds 1e-3. 1a3 RBF 1.0. Length scale bounds 1e-3. 1a3. Create a compound kernel using addition. Compound kernel. Kernel 1 Kernel 2. Create a Gaussian process regression model. GPR Gaussian process regressor kernel. Compound kernel. Train the model on your data. GPR. Physics. Y. Make predictions. Predictions. GPR. Predictix test. Points to consider. Hyperparameter optimization. Carefully tune the hyperparameters of each individual kernel within the compound structure for optimal performance. Overfitting. Be cautious of overfitting, especially when using complex compound kernels. Consider techniques like cross-validation to prevent overfitting. Data interpretation. Understanding the contribution of each individual kernel in the compound structure can provide valuable insights into the relationships within your data. Conclusion. Compound kernel is a valuable tool in the Gaussian process toolbox, allowing you to model intricate relationships in your data and achieve better predictions. By understanding its features, applications, and potential limitations, you can leverage this powerful technique to improve the accuracy and interpretability of your GP models.